Okay, I came back to the physics classroom to show you some cool things about electricity and magnetism. Here's the first thing. I've got a piece of white paper here, and on it I drew two rectangles because that's where I'm going to put a magnet. I'm going to put a magnet. These two magnets, okay, here, they attract. I'm going to put the attracting sides near each other. It's either a north and a north, north and a south, or south and a north, maybe. And now I'm just going to sprinkle some iron, little bits of iron on it, iron filings on there. And what that shows you is the field lines. So you can see, actually you can see on one magnet, you can see field lines go from north to south or maybe south to north. And then between magnets, you can see them also go from north to south. You can see them curving around there. All right, but if I flip one of the magnets, now it's going to be north and north, or maybe south and south. Let me put new filings so you can see that. Okay, so that now these are repelling. Take a look at the lines. In the middle, they move away from each other. This is just like a positive charge and a positive charge, where you have field lines that are going like that. It looks really similar to charges, but this isn't charges, this is magnets. Okay, now I want to show you this setup. These are compasses. You know, compasses are magnets. And you might notice that every single one of these compasses, with no current flowing through this clothes hanger, they're all pointing the same direction. See that? They're all going like this. This is the direction of the Earth's magnetic field lines. So the compasses are like little, like those little iron filings. They just turn so that they're lined up with the Earth's magnetic field, which, as you know, roughly goes between the north and the south pole of the Earth. So now what I'm going to do is I'm going to run some current in this wire, and now I'm showing you the connection between electricity and magnetism. I've got a couple of batteries here, which will give me about 4.5 volts. It's not a lot, so you're just going to notice a little deflection in the compasses. Ready, set, go. Did you see that? One more time. Ready, set, go. Okay, what you should have noticed is that this one deflected that way, this one deflected that way. They all deflected so that are now trying to form a circle around the wire. Of course, the Earth's magnetic field is still there, so they don't deflect the whole way. If I reverse the battery, though, and make the current flow the other direction, you're going to see the opposite deflection. Ready, set, go. Ready, set, go. And you see the opposite deflection because now the circle is going the other way. The circle is going the other way around the wire, looping around the wire. Okay, so iron filings and compasses can tell you there's a magnetic field there, right? The other thing that can tell you is a magnetic field sensor. This is hooked up to Logger Pro. If I bring it near a magnet, you see the number going up? Oh, can you see it? Here. Oh, now it's negative. Now it's less. Now it's positive. Okay, let's try this with something else. Instead of a magnet, no magnet, just current in a wire. Now this wire goes around and around and around in many loops. Loops, 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 loops. And the whole wire is coated so that it's not conducting from wire to wire, but it's conducting along the whole wire. It's coated with epoxy, which is like nail polish. Okay, so now I'm just going to put some current through this wire. Before I do that, let's check the magnetic field inside. Okay, it's basically 0. It's 0.05. It's small, very small. I mean, you're always going to measure some magnetic field, right? Because there's the Earth. But now let's put some current through it. Okay, did you see it go up? It's at least 10 times more. Now, take the current away. Now it goes down. Current. Okay, what if I check the other side? I'm going to put it in the other side. Here. This way. Okay. Put some current through it. Oh, now it's negative. Okay. What about on the outside of it? There's also an electric field on the outside and on the inside. And you can think about each one of these loops is like the single wire that I just showed you, where each loop has a circle of field around it, but all those circles add up to a big circle that goes in through the middle of this is called the solenoid, and around the outsides, looping around the outsides. So here's a little illustration. This is the solenoid, or the coil of wire. Each one of these little wires has a magnetic field wrapping around it, and together it wraps around all of them. So you have magnetic field lines that go like this through the center, and then also around the outside, like this. Okay, and that looks actually just like the magnetic field lines of a magnet. Here's a magnet, north, south. The magnetic field lines go from north to south, and they look like that, etc. Okay, here's another solenoid, a coil of wire, and I'm going to put current through it. And I want to show you that, if I put current through it, I'm going to measure a magnetic field. I'm not going to do that. I'm just going to show you the effect of adding an iron core. So this is a magnet. I can measure the magnetic field with the magnetic field sensor, but if I try to pick up a metal thing like a paperclip, it doesn't work. Watch when I put an iron core in the middle, just a piece of iron down the middle. Okay, now I can pick up those paper clips easily, and I could probably pick up even a string of them like this. Yep, I can even pick up 3, and it's that strong. So here's another example of that. There's an iron core with coils wrapped around it. We call this, when we add the iron core, we call it an electromagnet, and the iron aligns with the magnetic field and makes the magnetic field stronger. All right, so this is not connected. Of course, you need to connect the circuit before you have that sparked a little bit there, now that's magnetic. Oh boy. Yeah, I could probably even pick up some of these masses with this electromagnet. Yeah, but then if I disconnect it, it falls right off. Let's try another one. I'll connect it. See if I can pick up the 1 kilogram mass. There, 1 kilogram. Now I'm just going to disconnect the circuit, and no more magnet. So electromagnet is a way to have a magnet that turns on and off. Here's one of the first devices made with electromagnets. It's a telegraph, and you can imagine that this part is in San Francisco, and this part is in New York, and these wires go all the way across the country. And when you connect the circuit, see this one moving? Can you see that? Moves down. And if you connect it or disconnect it, you could send a message in Morse code. And that's how they used to send messages across the country before there were telephones. Here it is up close. So this is a magnet that turns on and off, and there it is right there. That's a coil of wire there. You can see it looks like a coil. It becomes a magnet and then not a magnet. Most large magnets in physics experiments are electromagnets. And here's Morse code. Okay, I showed you now a couple of examples of how a current can cause a magnetic field around a wire. But now I'm going to show you a different phenomenon, which is that a current in a wire going through a magnetic field, this is a big magnet, north here, south here. That current will experience a force when it's in a magnetic field. So there's no current now, but I'm about to connect it. Ready, set, watch the wire, go. Did it go down or up? Ready, set, go. Okay, notice which direction it went first. Now I'm going to change the direction of the current. So I'll just put make the current go the other direction. Now watch which way the wire goes. Ready, set, go. Ready, set, go. Hopefully you saw it go up. Oh, sorry, it went down at first and then up. Here's another example of that. This is an old computer monitor made from a cathode ray tube. So they used to look like this, where the beam of electrons shoots towards the front, and then it's guided along the front by magnets actually inside there. But if you put a magnet, you're going to notice that it affects the beam of electrons. It moves the beam. You can see that just by putting a magnet anywhere near the near that beam. You can redirect the beam. So this idea that you can run current through a wire in a magnetic field and it will cause a force on the wire gives us the concept that creates motors. So if I run a current here through this circle of wire, it starts to spin. You see that spinning because there's a magnet. There's a coil of wire, currents going through the wire, going through. Actually, I have this wire, I only sanded the top half of the wire so that it's only contacting when it's going the way that makes it, the force spins it in that same direction so that it's always continually spinning. I'll show you that one more time. There, a little motor. So here's a motor. If you put some current through it, it starts to spin around. If you take a motor apart, I've got one here that's taken apart. Take off the lid, look inside, you see it's just coils of wire and magnets. That's how you make a motor. Coils of wire in a magnetic field causes a force on the wire, causes it to spin when you put current through the wire. That's the idea of a magnet, of a motor. So you can see there's a motor inside this. When I put some current through that motor, it'll spin around. But this can also be used another way as a generator, because if I turn the crank, what can you see here? If I turn the crank, it's generating current in the wire. So you can think of some, I'm sure you can think of many different things in your life that spin around because there's electricity going through them, right? Just like when I connect the electricity to this and it spins around, that's a motor. And you can probably think of some appliances you use that spin around when there's electricity connected to them. I'm sure you have at least 3 or 4 in your home. The generator works the opposite way. When you exert a force on coils of wire in a magnetic field, you will generate current coming out of that through that wire, and that generates that is how we generate electricity in our power stations, in our power plants, where we, for example, boil water to create steam. The steam turns turbines. The turbines turn a generator, generate electricity, and those go to high voltage transmission lines, which come to cities and are step down for the voltage in your house. There are other types of power plants, of course. There's nuclear, but that also just heats water and turns turbines. Solar power is a little different if it's with solar cells. But most power plants of any type use some kind of heating of water to turn turbines, to turn a generator, to generate electricity. Okay, the last thing I'm going to show you. Okay, here's your last cool electricity and magnetism demo. This is a little homemade speaker here. It's got a coil of wire. It's got a magnet in the coil of wire, and it's a cup. That's it. You could make this on a potato chip. It doesn't matter, but you've got something that can vibrate, which is the cup. So when the current goes through the wire in the magnetic field, the wire moves. There's a force on the wire, and it vibrates the cup, and that causes sound. So let me connect this to my radio here. See if you can hear it. Okay, I'll disconnect it, and now I'll reconnect it. There you go, homemade speaker.